It's like you're put in that situation. I feel like every assembly
All right, let's get started. Cool. Come on, guys, let's get started. All right. Thank you for coming to the lecture. So today, as the title suggested, we're going to talk about timers in the embedded system. And you're probably going to guess that it's some mechanism or peripherals that helps you with keeping up the time, and you'll be correct about that. So that's going to be the main topic, but before we started, a few announcements and some other related logistic issues things. I guess what most of you are most concerned right now. We're going to have a review lecture this Thursday, so if you're not sure what we have talked about so far, consider come to the lecture. And we're going to have the midterm this Friday from 4:30 to 6:30 at those 3 locations. Again, you will be assigned to the classroom, one of the classrooms, based on, I'm actually not sure, probably your UMID or ID numbers. And yeah, please believe me when I say that it actually takes the teaching team more time to come up with the exam than probably most of you spend on study and prepare for the exam. With that being said, I will also say that if I get to choose, spend more time making the exam versus spend less time on review and take the exam, I will always choose making the exam. So I guess that's even between us. Enjoy. I already done my part, so now it's up to you guys. So, and the topics we're going to cover. Actually, let me first show you what a midterm exam is going to look like in case you guys haven't clicked on the practice exam we gave you. Basically, this will be what a typical midterm looks like. This is from previous semesters. There's some numbering issues here, but yeah, we're going to just ignore that. Basically, we're going to have a few multiple choices that covers across all the topics that we covered up until last Thursday, up until the interrupt and MVIC. And the short answer will be have some short answer questions. Typically you write a few sentences explaining your answers or write a couple instructions to demonstrate that you actually know the concept or filling some blanks. In this time, the short answer is going to be the second, and then the question like 3, 4, 5, it's going to be like 3 of the specific topic related longer question. So for example, say if we take the register and stacks as example, you will see something like, we give you a register and memory map, including the stack spaces, etc. And then we ask you, giving the sample code that we have, what's going to happen after each of the iteration, and then let you fill out what typically something look like is fill out what the memory or what the stack is going to look like after these events. So and then there's a big chunk of the time and also effort what goes to what we call like the design problem. They usually have like for the previous year, this one is a little bit longer. For us, we're going to only be like 2 parts, so it's slightly shorter than this. Basically, it's like one big problem, kind of like what you guys encountered in homework 3, the last question on homework 3. You will be introducing a new sensor or with some documentations or with some predefined functions inside, and then you're trying to figure out how do you get it work. This is where the fun part, basically you're trying to get what a real, I guess a real life machine or real life device works. Only under amount of, 30 minutes to 50 minutes, depends on how you distribute your time. And along with the exam, we're going to give you a data sheet every time. So the beginning part of the data sheet is going to be something that highly customized for that design problem, with the some of the function calls you might encounter, some of the registers, how it looks like, etc. And then down there, it's going to be pretty much the same across each of the some APP tables, time diagrams, and as well as the conditional codes, like the assembly codes for in case you have to write some of that. So this is what a typical data sheet will look like. So these will be essentially what you have during the exam. I know it looks like a lot, but I think once you're 30 minutes in, you should get much adapted to this. Yes, question?
Will the exact one for this exam be released like prior to the exam? The data sheet?
The data sheet part, so the question is about how close, how similar this data sheet was compared to our data sheet going to be compared to the previous data sheet. So pretty much the appendix are going to be the same. It's the beginning part where it's the design problem specific is going to be changed. So we will be holding on to the datasheet until the day before the exam for obvious reasons. But majority of the part, especially for anything that's before the design questions, the datasheet, it's basically these two appendix. Any other questions regarding the structure of the exam or the datasheet? Okay. Not sure because you guys haven't opened it or you already totally ready. So cool. That's some other things I would like to mention, which is I think very useful. The topics we actually going to cover. So assembly and essays. I don't think we will expect you to write a lot of assembly functions. You probably make sure you understand what they do and then understand where to put them. And you might or might not be asked to do a few lines of the assembly. It's not going to be something that we ask you to write a full program or anything. Because as far as I understand, we have a lot of folks who haven't taken the 370 as prerequisite, but are really eager to take this class. So yeah, this one is for you guys. We're not going to heavily test you guys on the assembly writing, but make sure you understand what they mean. And a little, all those little tricks that you do, immediate add, some things like that. For the ABI 2-chain, it's pretty standard. And then MMIO, the memory mapped IO, and APB and GPIO pings, GPIO channels that we talked about, input, output, different modes, and how do you connect them to, the P-select signal, the P address, if you want to determine the registers between one peripheral, as well as some other P enable, all these signals, how they work. And of course, we have the interrupts and MVIC. So this one would not be a long question itself. It's basically going to be embedded inside of the multiple choice and short answer because I think it's relative new content, and some of you guys before the exam might already done the lab. Some of them have not. So just to make it, I guess, fair, so we're not going to heavily test on that. But you should know all the basic concepts at a multiple choice and short answer level. So, yeah, and we will test a little bit on the basic electronics. It's not going to be too much. Pretty much just different modes of the GPIOs, pull down, pull up registers, open drains and stuff. We're not going to test too heavily on that. So, if you haven't take, is it 270? 270? Don't worry too much, but yeah, just know the basics. Okay. Any questions so far regarding the exam? No questions? Yes?
There won't be a cheat sheet, right?
There won't be a cheat sheet. We will have basically the data sheet for you here. Yeah. Any other questions? Yes?
Is like the drops of electronic section you stick to the multiple choice?
I think so. Multiple choice and short answer, maybe. Yeah. I don't think it's going to be in much of the, I don't think it's going to be inside of any of the long questions. Any other questions? Okay, yeah.
So how many pages of new information will there be? So there's a portion of the exam that is about 25 points in the last question. And there's a certain number of pages that are new that we'll also have to read prior to answering that question, correct?
You're referring to like the design question, I assume. Yes, so I guess you have to plan strategically, if you're running out of time. I don't think you should run out of time based on, but I will know today after my teaching meeting. We will know exactly how long it took our IAs to finish our exam draft. So I have like a better understanding of what's the timing of the current version. But generally speaking, I believe for the design questions, you do have to read a lot of stuff at the beginning, but I believe once you read through it, the write up the answer and the solving part is actually doesn't take that long. As long as it's like kind of like a steep curve that once you get it through, then you're good to go. So I would definitely encourage you to still work on the design question and not spend all the time on the short answer or multiple choice or like the previous questions. Yes?
Could you do an example one of those problems on Thursday's lecture?
The design question or? Okay, sounds good. Have you guys looked through the previous 2 practice exam? Any specific ones you wanted to go over? Or just either one is fine?
Either one's fine, but if you could find a new one, that would be cool too.
Okay. We did come up with a new one. I can't reveal that to you. But yeah, it takes a lot of time for us to come up with a design problem, unfortunately. So I'll pick one from the previous 2, and then the more, okay, I'll promise you I'll pick the closer one. How about that? Okay, cool. Any other questions before we go into the magic timer? Okay, perfect. Cool. Yeah, before going into the timer, a quick, a review from the previous interrupts because they kind of overlaps a little bit. Basically, we have the peripherals that hardwired to the core that each assigned a number that triggers the interrupts, right? And this is like a quick flow how it works. Basically, we have the main program, it's doing its own thing, and all of a sudden, something happened here. And then a bunch of things got saved in the stack, and then we go look at the interrupt vector table to determine what's the address of this, what's the address stored at this interrupt location, and then goes to the ISR, the service, the handler functions, and do a little bit things, and then you unstack the stuff back to the core, and then it keeps executing from that point on. It's like a basic workflow. And some of the steps that the ISR took, basically, let me just get them all out. So basically, the peripherals, in our case, most of the time, the peripherals will raise the interrupt signal, and then the MVIC will decide which interrupts to process next based on the vector table. And then the core will complete the current instruction. Normally, it completes the current instruction before it goes to the stacking. There are some edge cases you could override, but override that, some of the system exceptions, for example. But normally, it finishes the current instruction. And then it does the automatic save to the stack. It's done at a hardware level. Basically, you will be stacking the program counter, the PSR, the program state register, and the R0 to R3, the caller saved registers. R12, it's one of the intermediate, it's one of the registers that usually used to store the intermediate calculation values. So, those ones are typically also saved between the function calls. And then also the link register, just in case that the function is actually currently inside of multiple layers or at least more than one layers of function calls, so that it knows where exactly to go back to and then go back from that point. So those things will be saved, and then we'll go to the new location of the functions, which is the handler function, and then set the PC to that vector counter, and then update it to that. After it finishes, you go back to the main program. The whole thing can be as short as 12 cycles in this case, if the read and write does not take too long to process. Like it's not read or write to any of the external devices, for example, or the read or write does not take additional cycles to process. For example, the ADC analog to digital converter. So these are like a very typical steps and how long it will usually take. So this is a very quick review, basically, which will move on to the timers, something that sits underneath a lot of times to do the handler or like how they how to trigger the interrupts, so to speak. It's pretty much the timer. Essentially, it's essential to implement delays, as you imagine, measuring like the time intervals, how long a particular process have taken, or how long a particular, I guess, peripherals or devices have been running. And it also generates PWM signals we'll talk more about that in the later part of the lecture. And you will probably use that pretty extensively in your final projects. And also it's used for like triggering periodic events, which is, you can essentially think of them as periodic interrupt, so to speak. So these are handled by the timers. And these are some like additional stuff if you want to read more in details, like the developer reference menu that's out there online, and like the textbook that we have. We don't have an official textbook, but one of the recommended reading that have a general purpose timer chapter inside of this book. Welcome to read that if you want to like more information. Or I suspect most people are going to go to one of the YouTube channels and then watch it through. That's also welcome. So a little bit background on the timers and clocks in general. From like I guess most humans' perspectives, the timer, for example, in the smartphone, it basically provides like the war time and determines, if you're trying to have like alarm or you're trying to make a stopwatch to basically set a timer or measure for a certain amount of things. The embedded system can also do that, but it doesn't keep tracking of the war time, like the time you typically get, I guess, from the satellite nowadays. Previously, it's from some of the crystals on the system. But basically, in the perspective of the embedded system, it says how many time in terms of how many clock cycles, for the instance, during each of the program or each of the instances it's running since it's being turned on. That's how they keep up with the timer. There are some, I believe there are some modules nowadays like ESP32, they have Wi-Fi modules on it, and then they can just grab the time from the Wi-Fi router if it's got connected. But even with that, internally, it still use basically the internal, the hardware timer that counts the clock cycle. They do a little conversion on like a higher level rather than from the software level. And why they're useful? These are something we could work with in the embedded systems that will require such functionalities, or why they're very important for like timings and how fast they rotate, etc. You will see the PWM come up a lot. For example, like the servo motors that we talked about, I think last lecture or 2 lectures ago, as the components of the day, as well as normal DC motors and like RGB LEDs. The reason for that is most computers are really bad at analog. So if we say we want the servos or motors to like rotate for, for example, at 30% of the rate for like X amount of time, if the signal is analog, it's actually quite hard for the system to handle. So for that, we actually do this on and off thing to make a percentage of the signal out of a on and off state, which is essentially the PWM signals, which we will talk again later in more detail in later slides. But like these are why it's very essential, like the timers essential in the embedded systems, apart from obviously keep the time for how long the program has running. You can kind of think that the computer's superpower is keep tracking of time, and if you can kind of make an analog problem into a on and off timekeeping tasks, that makes everything much simpler for the perspective of the computer. Yeah, a little bit more on the timing function. What is happening today? Okay, so these are some typical functions in the computer systems. They periodically interrupt the CPUs to perform tasks. These are, for example, for those. If you want to keep monitoring an event, for example, like the temperature or pressure sensor, they typically are routed that or programmed that you check it every 1 minute or so. These things, you don't want to like keep checking them because we have only limited amount of computing source. If we just do that one sensor, then the whole system got lagged, and there's not much to do with with all the computation powers. So things here we do is we have the timer to be worked as like a periodic interrupt that keep interrupting at a given time that's being set, and then that will give you the reading at that rate. You can design that. You can decide what's the frequency of the reading, of course, based on from like hardware level or software level. And it also provides accurate time delays instead of like software loops. There are different ways to do this. Obviously, you can essentially write a piece of placeholder program that does kind of nothing there, or you can just use like a timer to have the program to be kind of paused or delayed for that amount of time. It's more like power efficient, and it's more accurate as well, rather than if you write those pieces of filling codes, because the program can be interrupted at different times, and those might cause asynchronizations between different peripherals, etc. And of course, one of the big parts to generate pauses and periodic waveforms, which, yeah, I feel like this is the third time I promise you I'm going to talk more about this in the next slides, but we will talk more about this. And it also measuring the duration of an external event here. You can think about we could use the amount of time it's being turned on for each motors to kind of know how much power is being delivered or how many terms it's being turned, so to speak. So these are the things that the computer essentially tracks rather than what it actually tracks. Except for some cases, for example, the servo, they actually have its own feedback loop. Then you have some rooms for arrows, but for most of these devices, it's going to be basically just tracked by the time. So yeah, this is like one of the examples, just how measuring time on an MCU works. Basically, we will set a timer, which acts as an interrupt to go off every t second. And then every time we enter the interrupt functions, and then we do the tasks. And usually it's very short, and then the includes, and then every time that happens, it clears out one of the flags and go back. The flag was usually stored in one of the registers for the timer specifically. We will also introduce that in the later. But basically, this is a very classic use of timer for periodic occurring event. Any questions so far on the timer, like the background and how it internally? Well, we haven't talked much about internally, but like on an abstract level, how we could use them as periodic interrupts. Okay, perfect. So how do the electronics actually detect the passage of time? Like, how do they know if the time has passed? Any guesses here? From like a hardware level. How do humans get, we get it from like nature world, sunrise down, not very accurate, obviously. And then later on, some genius figured out to put a stick on the ground that gives you more accurate. And then some part later, more genius people found out, apple fall from trees and all that. You go to the, the story. But how does the electronics know? Yes.
Periodically vibrate in that pattern will add up to a second, and that's how we keep track of time.
Mm-hmm. That is very correct, actually. It's, I guess 60 seconds was not, we don't need to use that. But yes, it's pretty much crystal vibrating crystals. You can think of them like a spring or like palladium. So it kind of stores the energy as kinetic or and also potential energies. You have the oscillations dependent on the length and the mass of the spring. So in the case of the crystal, it's actually storing the energy in terms of electric field and magnetic field. So they are quite accurate. Usually we have the crystal, and we will call them oscillators, and counters working together. So they will be measuring times, intervals, generating periodic signals inside, which is what we're going to talk a little bit more in detail here, the anatomy of the timer. So yeah, we have some crystals there. Basically, it's the external physical world that has, been, it's very hard to put like good crystals that onto the silicon directly at the moment, or not very cost-effective ways, at least. So typically, most of these clocks or like timers are still attached as a individual components to or like external devices on the board. And you usually have some kind of lock source internally for like additional timers if you don't want to use the external crystals, but they're not as accurate. The external crystal, like the external timer, is still I think the go-to solution for most of the events at a lower frequency. And that's something that looks like that. If you, in the future, see a PCB board have a little piece of metal on it and some number on it says M something, that's chances are it's one of the timers that used to drive some of the devices on board. And yeah, there are some clock drivers and feedback loops that happens here. We won't go too much detail here because that's too much hardware involved. And then we have a prescaler. So basically, usually those crystals, in terms of the core, it's kind of slow, right? Or like kind of okay. But in terms of most of the programs, most of the interacts, we want to deal with at a human interact frequency or at an embedded system handling speed, chances are they're pretty fast, and we don't really need to have all those cycles to be triggering all the peripheral devices. So we have this prescaler that basically divides the clock frequency to achieve like longer time intervals. Except, for example, if we have system runs at say 40 megahertz, and we have some prescalers, we can scale it down to 4 megahertz or like 1 megahertz for some specific peripheral devices on board. And then we have the counter registers. It basically, it does very simple things, but it does it very well. Basically, it does increments or decrements or both at each of the clock pulses. And we typically use this to measure measuring the duration of the time of each of the, like how long the program has run, or you use that to keep track what's your periodic interrupts state are at the moment. And then we have the capture or compare register. It usually holds a predefined value, and then when the counter machines matches this value, then something occurred, something happened. If that sounds quite familiar with you, you're probably thinking about the right thing, which is interrupts or some of the output signals that can be used for this method to be triggered on like a hardware level. Next, we'll be entering like the realm of the software. First, we will have like a lower level timer subsystem. This is typically written in like C or compiled C or assemblies that handles the interface between the hardware timer to the software you work with. Then we have the operating systems that going to do some abstraction of the time and virtualization. So the time abstraction basically refers use of the software level or APIs to hide the hardware-specific details of the timer. So imagine we use different type of crystals or different types of timers down there, but after that layer, it's going to be look like the same from the core or from the program's perspective, right? Because all those details are being abstractionized. So, and then we also have the virtualization of the timer. This virtualization is a software technique that allows multiple applications to share a single hardware timer. It basically provides like a virtual timer to different tasks. This is, again, like a very convenient way to have only one timers, but you can use that to control multiple different applications or different devices at different frequency. So this is the virtual timer here. And at last, there's like the software application layer, which where you guys will mainly be writing the programs for, and that's where the layer that talks to the outside world or the users, basically. Any questions on this so far? Okay, sounds good. Yeah, I hope this is pretty straightforward this is just what's inside of a timer structure from the very bottom hardware crystal all the way up to the program level. Yeah, we will talk a little bit more detail for the crystal part first. So this thing here is usually what you would see as like a crystal or crystal oscillator. This usually have some load capacitors on both sides. The value of those are basically you should just refer to the datasheet. They give you pretty good references on what's the load capacitor that you should use. And these, on a side note, these type of diagrams are pretty typical inside of datasheet. It gives you some passive components you usually use or usually add to these components to achieve certain configurations. Chances are you have different configurations, but just choose the ones that works the best for you. And you should always, reference to datasheet for those configurations. Sometimes these numbers might or might not make sense to you, but just trust the datasheet for most of the time. And then we also have, I believe, yes. Oh yeah. Also, because of the crystal is actually quite accurate, so you don't have to worry too much about debugging it as long as you follow this diagram. So if something's wrong with your system, chances are timer is not one of the major sources that cause that. As long as you follow it's probably what you wrote in your program. But so yeah, there are also like different types of crystals. Typically, ones you can see here. Different ones they usually at different frequency. The very common ones that used for track of like human time is the one that typically runs at 32K.768 hertz. If you do the calculation, it's actually the number like 2 to the 15th, 2 to the 15th. So basically, you have like a 15-bit registers, and then you will have like precise 1 second per period for this type of crystal. So which is like very convenient, and that's what typically used to track the human time. And those things are converted into year, month, date, hour, minutes, etc. And of course, all these things are accessed through the same as any other devices, through the MMIO, the GPIOs. But chances are, for example, this 32K or 33K timers here, it's probably going to be too low to run the rest of the device, right? Oftentimes, you will need something like megahertz or hundreds of megahertz for the core to operate correctly or operate fast enough to keep track or keep up with all the computation it needs to do. So how do we do with that? There are other sort of like clock sources. For example, this like the surface acoustic wave resonator, the SAW resonator. Basically, it's usually for like higher frequency needs. It's type of electric components that uses the surface acoustic wave to generate and filter the precise frequencies. It's widely used in, I think, wireless systems, RF transmission communications, as well as some other applications that needs the higher frequency and stable higher frequency applications. They usually run from tens to like hundreds megahertz. This is also very accurate. The limits here usually it doesn't offer a lot of frequencies for you to choose from. It's essentially it's getting like very hard to manufacture at this level to have a lot of options for you while still keep the price at a like reasonable range. So these two are very hardware, still quite accurate, used typically for different range of the frequencies. And we also have something called like internal clock sources. Basically, these are like digital digitally connected, controlled oscillators. It's internal to those devices. You can make an oscillator use like a bunch of inverters as long as you have the correct number adding up along the way. So it does give you the luxury of a lot of choices over different frequencies because they're kind of implemented based on your own choices, but they also have the trade-offs of being less accurate. For example, these, like in our system, like the AHB and APB bus, the clock, it can speed up to like 120 megahertz, but the external data, like the external timers we have is only, I believe, 48 megahertz. So how does that work? I'm going to just give you the answer. Basically, it's something implemented within this internal clock source, but they put a phase lock loop on top of it. Essentially, it's a phase comparison. You can think of it at each edge of the clock, between each edge of the clock, it synthesizes a higher clock frequency based on the first frequency by pushing multiple cycles or multiple waves instead of this one cycle. And after a period of time, if the phase matches between these two signals, then they consider it as a stable, higher frequency signal. Like, for example, each time it's just doing like a little bit calibration there, but each frequency or each clock cycle of the hardware timer, you try to push like 2 or 3, like say 3 events in. And after a few iterations, after a small amount of time, you kind of find this sweet spot where these two signals phase are aligned. And when that happens, they just use that as the timer, as an internal clock source. Obviously, it's going to be a bit less accuracy, but you know, we always going to have some trade-offs here. But this is for if you want to have like a higher, even higher frequency that's higher than what the hardware is able to offer. Any questions so far for those different types of? Yes.
Do we use those for clocking the CPU?
Do we use those to clocking a CPU? I don't think so. I think for the CPUs, it also have different modes. So yeah. Any other questions? Okay, cool. Yeah, so they have like this clock distribution. We don't have to worry too much about this. Just recognize its existence. Basically, we have like multiple clock sources, and in case in the final project or later in the class, you need to use different and specific frequency for whatever reasons. These are some of the tools you could use. Yeah. I think I think if some of you guys do want to use like a VGA monitor or projectors, they typically require very specific frequency. So some of the tools here might or might not be handy for your application. But yeah. Next, we're going to talk about like the prescaler and counter. It's pretty much being like a clock driver. We're not going to talk too much about the clock drivers because it's not the main part of this class. This is what a counter typically looks like, or like prescaler and the counter together looks like. Firstly, we have a clocking from the hardware level, and then it goes through the prescaler, which does this, which divides the clock frequency to achieve like a longer time intervals for more controls over the system. And you will see that it's on the equation here, we use the prescaler +1 as the divider down there. The reason for that is, I think in the history, a lot of people just sometimes put 0 to this number and it causes all kinds of problems. So the STM just decided that we're going to just make it +1 so that none of those system failure are going to ever happen. So yeah, just remember that whatever number you set to the prescaler, it's technically always +1 when you're actually doing the dividing. And then it goes to the counter, which is a special register, like time counter. This counter runs freely, and if it enables, it just automatically comes up or comes down, or comes up and then down. They have different modes to choose from, and then it's just driven by a clock source, which in this case is the clock that comes from the prescalers. So as long as it's been enabled, that's all it does, and then it does it very well. And then typically, whenever that the counter comes to a specific number, some interrupts happens, as a periodically interrupted event. Those things will happen when the certain amount of time has passed. And then it will basically rise the timer, and then your core knows that something's happening. It goes to a little bit of things, and then at that moment, it also tells this little ARR, which is a auto reload register. Basically, it says that whenever the interrupt goes off, that's when you should reload your counter to the previous, and then do the counting again, and then keep track that when's the next time to the same event going to happen. And this happens before it goes to the interrupts, so that they are like very accurately timed every time, unless something happened during the interrupt that just cause all kind of delays. But it has like one layer of protection here. And let me show you what it looks like for like a clock divider on a hardware level. So it's, can you see that? Okay, let's make the speed much faster. So basically a bunch of D flip-flops. If you say we have like 4 of them, and then these are the output signals. The beginning one is the actual clock, and then every time it goes through it, because of the Q and not Q together, it kind of divided by a factor of 2. And then at the end, we have, just depending on how many you connected towards, each of these output is gonna be dividing the signal to by a factor of 2 here. I hope this is pretty straightforward. Okay, perfect. And then we have so basically just put into context, we have the clock divider by a scale of 2, and then with the once we add a counter to this, it gives us even more control over it. So basically, we can divide the counter clock frequency. If we use like a 16-bit counter, then we have like a much wider control of what's the amount of the frequency, or what's the target frequency we want to use. Let me again give you like a quick visualization here. Oops, sorry. So we have the thing we just had before, and then we added that to a counter. So essentially, each of these counter output became one of your source that you can use from. So on top of whatever you had down there, you also have an additional 16 steps of the frequency of the factors you can use based on the clock input. I hope this is also pretty straightforward at this point. Okay. All right, cool. So, the counters here, you typically have like 3 different modes, or like a few different modes. You can come up, come down. You can hold the value there. There's also a mode to come up and then down. This is a more accurate internal look of the counter, but it's not the main point of the class. All you need to know is how it behaves, basically. You connect it to a counter on top of whatever you already have from the previous dividers. You give you a lot more controls over the factors you could achieve based on the input clock. So then we have the prescaler and counters figured out. Next, we're going to look at the capture and compare here. They are basically these 2 different ways. We're going to talk them one by one. So So first, capture here. Basically, it's trying to figure out or like measure how long something takes or have been happening, essentially. And for the capture, as you will notice, you probably guessed from the name, that's the compare. You probably guessed from the name, it's basically a clock source that, just sitting there waiting whenever the timer or whatever the number that comes in matches a preload value inside of this register, it got triggered and then do something. Let's go through like an example for a capture. For example, you have like a fan and you want to know how fast it spins. One way to do that is obviously you have like a GPIO interrupt every time it completes the rotation, and then you just keep tracking how long it takes for that, or just keep tracking, how many times within a amount of time, and then divided that, the speed of your fan. It's kind of waste of interrupt there, and also waste of energy, so to speak. There are other ways to do it with the counter and with these capture and compare registers. So basically, we will have the timer noted immediately how long it took during its rotation and generates an interrupt, and then reset the timer immediately. So this does not have to necessarily go interrupt what we have in the main program. It's just like whenever the main program wants to know what's the current rating or current speed, they can just read from this register or read from wherever this value is saved and then get the current time or current rotation speed, as opposed to actually interrupt to or like buy a GPL to check every rotation or so. Okay, and yeah, the timer can also be used for like input capture. So basically, let me just have it all out. Yeah, so basically when a specific external event happens here, the right edge of the external signal on GPIO pins, for example, the hardware will automatically copies the current value of the timer counter and then to the CCR, the compare and capture register. In this case, it's the capture example. And once the core is ready or have time to, or wants to look at this, it will just always take a look here to know what's the current stats of this device, instead of doing it every time through the actual interrupts. And any questions here? Just okay, or everyone just focus on the midterm now. Okay, cool. Yeah, we have also different modes on this capture mode. It's pretty standard. You can have, it's been monitored on both, for example, both the rising and fading edges. And this will give you a time inside of that, inside of a register. Or you can also measure only like rising or only fading edges. Just depends on what your specific applications are. Also, something that you might just want to keep in mind, the actual ward, like the external ward, is quite noisy. So oftentimes it will have those weird wiggling signals that might or might not interrupt, messes with your counting ability or input capturing ability with this CCR register. What the hardware level does is essentially like the signal could very much look like this. Basically, with the hardware level, they do have an additional like a counter filter. That's something, just keep track and make sure this state or this edge or this thing happened for some amount of time, and then goes into record that. This is the pre-filtering or like filtering down on the hardware level. It's obviously not as sophisticated as the software or like algorithm level filtering, but it's good to know that these things exist, and they did like a pretty reasonable good job for a lot of the outward noises. And all of these will be in the datasheet, that the one that you specifically work with, if you are interested to know what are the type of pre-filtering that has been done before these CCR registers. And that was for the capture. And then this is for comparing. basically, as we mentioned briefly in the like the motor control, for example, it would be great to do like a, oops, giving it too much. Yeah, it would be great if we can somehow do this in like a linear fashion to give it a linear signal on how much or how powerful or how long these, usually like how powerful this motor should be rotating to. However, it's not great. The computer in general not great handling like analog signals, and it's become like messy. And it turns out that the better ways to do this is actually for it to switch between like on and off, or like max and off quickly. And then we use the average of that, or duty cycle, so that we get a measure of how much power or how much triggering was sent to the specific device, as opposed to purely use like voltage to do that. Yeah, so basically these are the signal with a certain duty cycle and frequency. And how do we actually achieve that? This is where the compare functions that comes in play. So basically we have configured the timer into, in this case, the compare mode, and then we put in some fixed value in there, and then tell the timer to either start the counter at that value or just start from 0 and then count up or count down. And whenever it occurs at a certain, say if we ask it to count until 6, whenever the 6 is reached, something happened. And yes, also when the timer is configured to generate the output signal, the hardware will consistently compare the counters with the value stored in this CCR. And then whenever they match, they output something through like GPIO pings or something, and then have some event triggered by that timer. So a little bit more details on what are the compare modes you can choose from. Which basically control things to, it allows you to control things to be high if something happens, or low, or you can force it to be always high or always low, just based on your configurations here. This is generally for the output comparing. That use that to control most of our cases control a GPIO signal to a device or to the outside world. Any questions so far? Make sense? Okay, perfect. Yeah, we have like different ways for these counting to happening. We can, as we briefly mentioned before, we have like count up, count down, and you can have like count up and then down. You will find this like with these functions, you find it much easier to do the math and control things, and then it gives you like great flexibilities on however you want to deal with this device. And the reason they have this come down and up and down is because just in case, say we have a 16-bit register here for the counter, and then you run out of that, and then by using this, it's essentially doubling your range of counting, and gives you like additional flexibilities while control any of the specific hardwares. Just make sure that you read the datasheet of whatever device you're trying to interact with, and then have set the signal, or the counter in this case, to be mapped to whatever the input range or the performance range that it should have. So this is when we have like a multi-channel output. So to start with, we have a clock source. We have like multiple clock source. As we mentioned, we have internal ones, external ones, and some of the internal triggered fancier ones. You chose whatever the clock source you want for any peripherals or any devices you want to interact with. And then you have your, this is like a general workflow on how it gets from the hardware level to whatever you're trying to control on the output. Basically, you have the clock sources, and then you have your prescaler registers and your counters to choose the desired frequencies that you want this timer to be. and then it goes to a multiple parts of the capture and compare registers. This was essential for like the PWM signals. I feel like I mentioned that a lot, but basically it generally gives you like more flexibilities, which we will see in the just next slide. Any questions on this so far? This is like a very high level how these things got connected together before it goes to the software level. Basically, you have the timer, the raw signal timer coming, and then you have the prescaler divided by 2. Depends on how many D flip-flops or how many flip-flops you have on that prescaler. And then you have the counter registers that give you even more flexible controls and give you like a continuous factor of the frequencies or of the periods, well, it's the same thing, frequencies that you're able to choose from. Okay, all good? Sounds good. So yeah, now we're going to talk the PWM, the pulse width modulation, and how they work. We could, I guess, go through this one quickly as well. This is like a very small example on basically the turning on and off an LED based on the duty cycle of this program, of this circuit. It might be a little bit hard to see because the frequency right now is not that high, but imagine if we have the clock to be like very, very fast, faster than whatever your eye is able to refresh. And then all of a sudden, this on and off becomes the brightness of the LEDs. And then that brightness, in this case, is corresponding to the how long the signal is on at any given period, which is the duty cycle. Yeah, I think this simulation tool is not great for actually visualizing the brightness of the LED, but I hope it gets the idea across. And I think you guys all watched the movie before. Just imagine this go like 50 times faster, and that became actually how bright this LED is. Okay, yeah, just have to take my word for it. So yeah, if we look at like more fundamentally, this is essentially what we're trying to do, right? We have a counter, and then we have a system of output, 0 and 1s here, 2 graphs here. And then we're basically trying to create a pulse that's up for a certain period of time and then low for a certain period of time. So how do we exactly do that? First, we will set the timer, or like the counter in this case, the upper part. Basically, oops, okay. So we can configure the timer to the counter to repeatedly count up. This is, for example, we give a number of 6 that it basically counts from 0 to 6, 7 steps, and then it would just keep doing that until you kill the system. And then the auto load register, the AR here, it basically holds this 6 value, and then when it starts counting, you will see whenever it reaches that number it's stored there, which is 6, it goes down, and then something happened to the trigger, and then the signal will be up for that amount of time, and then goes down again. So this is for like an upper counting mode. You can, yeah. So basically, it just keeps counting up, rolls over, and then whenever it exceeds 6, it got resetted, and then back to do the counting again. And whenever that happens, the recounting happens, the overflow happens, something's triggered in this case. There are another register to give you further controls. It's called the RCR, the repetition counter register. In this case, it's set to be 0. What this does is basically have additional counter to count how many periods this has been, or give you a number, like this should happen every how many periods. For example, if I set this RCR to like 3, then this counter, up counter, 1, 2, 3, it's only going to have this one signal up instead of have all 3 of them. Does that make sense? It basically gives you even one additional control over the amount you have to give another counter on top of how many counters you could have instead of the counter register. Does this make sense? You just imagine like we only have limited bits on each of the registers. So in order to have more of these controls, we sometimes add more layers to the hardware. But I hope these make sense to you guys. If not, well, you're not going to be tested on the midterm. So yeah. So how do we actually calculate the periods here? We basically gonna just based on the clock periods that the input has, and then add 1 to the AR because it counts from 0 to whatever that number, and then you times that number. It gives you the current periods of the clock that's being generated, or of the signal that's being generated. This is under the assumption that, of course, the RCR, the repetition register, is set at 0. If we have numbers, then you just time that by that factor. Okay. And that was the upper counting. We also have the down counting. It's pretty much the same idea. It just counts from a auto reloaded value by the ARR before the sets here, again 6, and then always come down to 0. And after it reaches 0, hardware automatically reloads the counter from the ARR value, basically go back to 6, and then do that again. And every time when that happens, it generates a counter underflow event, and an updating event happens. In this case, a periodic interrupts that does little bits of something. It's pretty much basically it's very similar to the upcounting, and then the formula to calculate for the period, it's the same as the upcounting as well. And as we briefly introduced, there's also this upper and down mode. It's actually called central align mode, just in case like 16-bit of the counter is not enough for you if you want to have like more controls. And in this case, the formula will be like 2 times ARR and then times the clock period. I hope this is straightforward math. Okay, or any questions? Please don't be afraid to ask. Yes?
Does the CCR have to do with this?
Does the what, sorry? Oh, RCR?
The CCR.
The CC, you mean this one? The repetition? This one?
The compare and capture.
Oh, the compare capture. Yeah. It's essentially, this part is what the compare and the capture are doing. You set a value to it, and then every time it reaches 6, it does something. Well, this is more straightforward. Basically, every time you reach 0, it triggers a underflow, and then that became your flag or became something that's triggered. In this case, you can decide, but in this particular case, it's triggered by both overflow and underflow. But yeah, you have the freedom to set how it's being triggered. But in this one, it's handled in like the hardware level. So these two are automatically it's determined by the hardware. You don't have to have additional piece of code to tell that GPI or that register, etc. You have to do this however, you just set it once and then you always do that without causing an interrupt from the core. It's just kind of like interrupting itself and update itself. Hope that makes sense. Okay. Yeah. So that's how we set up, I guess, the ping part. So how do we control when these things go on and off, which is the actual output from the pings. Let's go again to this upcounting mode. This is called like low true mode for the PWM. Basically, it's fairly straightforward. Basically, we have like a CCR here, the capture compare register number set here in the control mode. Like the compare mode, and then that takes one value to the to interact with the counter. So previously, that was all happening in the counter. Here we add the capture and compare register. I think one of you guys just asked about this. So this is where they step in, and then that value here is going to be used to determine what's essentially the threshold of which part you should be used as a high or as a low. In this particular case, we set it to be 3, and it's in the low true mode. So basically, anything that's below the number of 3 became high on the output. Anything above the number of 3, it became a low in the output mode. And the formula for calculating the duty cycle here is basically the amount of time or the amount of count numbers in this case on the high divided by the total amount of the AR, the auto reload counter, plus 1, because it counts from 0 to that value. And then in this particular case, it's 307. So, and how do you calculate the periods? The periods here, it's pretty much the same as before. You just calculate it as 1 plus the AR times the clock periods of the input. In fact, these things, in practice, these things, you might wonder, why do we have 2 things for these? Because in practice, these periods is set once, and you usually don't change that after you set that for that PWM. It's the duty cycle that it's much easier to change and then also get updated easier. So that's usually what we use to change the amount of power you want to, say, drive the motor, or how much you want to turn a servo. And we just set the periods once, usually, and then let it run in the background. Any questions on this? So essentially, counter and compare and capture register working together. In this case, it's the compare mode. Any questions? Okay. And then we have the high true mode, which, it's pretty straightforward. Anything that's higher than that becomes the high. Anything that's lower than that becomes low. And then the calculation formula, it's just 1 minus that, and the periods calculation is the same formula as before. And then, as I mentioned, whenever we want to change the duty cycle or how much power is being pushed out to control this peripheral or this device, external device, we just usually change this CCR register, the compare and capture and compare register number. In this case, we change it from 3 to 5, and that gives us a duty cycle of a different value with the same period. Does that make sense so far to everyone? Okay. And then, we also have this central aligned mode, which is, I hope, pretty straightforward. It's essentially doubling the amount you could have above if we do like the high true mode. In this case, the previous calculation is slightly different. As we mentioned before, it's 2 times the AR times the clock periods. And then the duty cycle here, it's essentially, within each of the periods, the amount of time or amount of counting numbers above that cutoff ARR number divided by the total. And then that gives you the duty cycle. Any questions? Okay, cool. Yeah, let me just get through the next few slides. Basically, we have the multiple capture and compare registers. This is so that we can have essentially one timer and to set up one specific period, and then you're able to have multiple duty cycles. Remember, we showed this a few slides before, and then these different CCR registers, by setting the different values, we essentially have one timer control multiple devices. Say if you have motors that connects to different wheels of a tank or a car, you can determine how hard each of them should turn individually, rather than use. I guess you can use differential, but you could also just control them individually so that you can achieve some cool maneuvers like spinning around the spinning. Yeah, instead of 3-point turn, you do like a circle kind of turn. But anyway, yeah, we can use this, and then because they all use the same timer essentially, they're pretty much almost perfectly synchronized to each other, which is also like a big advantage especially for any of the timing sensitive tasks by using one timer for multiple controls. And some just even more details, you could do it by like left edge aligned, right edge aligned, and also central aligned based on the different modes we have. But these are like very implementation details. If that one cycle actually matters to you, if you want to have like perfect synchronizations, yeah, just make sure you have them aligned at a cycle to cycle, edge to edge point curve. There's also another like mechanism to deal with potential change, like sudden changes in terms of sudden changes inside of the duty cycle. Say if you have the duty cycle set at 30% at one point, and all of a sudden you change it to 80%. What happens to that first cycle that changes there? You're gonna have like a asynchronized, or like not sure how much higher that one cycle is going to be. That might cause asynchronization with the remaining of the system. And the PWM or our system have something called this auto reload preload enable, this one bit to control that. It basically determines when or whether or when we update the value from the ARR, the auto reload register, based on the current stats of the timer. So we will only update it immediate or after the next update event, so that they can still be synchronized even after you change the duty cycle, wherever point of the time that occurs. And just some more details you can go through from like the data sheet. A lot of the details, chances are a lot of them you don't need to use, but it's good to know. And for example, these things. And this is like a bigger diagram of how actually the register level looks like in our STM32. Feel free to read it if you want. And yeah, quick recap of the lecture today. Basically, we talk about the timer, the capture and compare registers, and then we talk about at the end how the PWM signal is generated, working together with the time module. So this is the end of class. If you have any questions, please let me know. Come down to me. If you have any questions regarding the exam, come to my office hour tomorrow, or get one of the TAs in the open lab session. Good luck, guys.
I'm confused with multi-bound bytes. Because I feel like each memory was 4 bytes, so where did the numbers come from? So I thought it would have been doing the numbers, which I'm confused why I do.